The types of inference problems that we're dealing with can be broadly classified into two types: supervised learning problems and unsupervised learning problems. In a supervised learning problem, there is some supervising output. That is, we're trying to predict some output based on the data that we have. Two types of problems that we deal with are classification and regression. In classification, we want to classify a data point based on its attributes into a bunch of categories that we know from history. In regression, there is some continuous output that we want to predict given attributes of a data point. In unsupervised learning, we're not really predicting anything. We're just trying to see what the relationships in the data are. So, clustering is an example of an unsupervised learning problem in which we try to cluster data points that are close together based on some attributes. We'll be focusing on regression for this module. What are we trying to learn? In regression, we believe that there is some output y that can be predicted by input values x1, x2, x3. These are attributes of the data. For example, if you're trying to predict housing prices, this might be the location, the type of neighborhood, the number of schools in the neighborhood, etc. We want to learn this relationship for two reasons: either to make a prediction or to draw some inferences. Okay, let's see how we think about our data. We think about our data in terms of two broad categories. One is the input values, which we say are x1, x2, x3, x4, and so on and so forth. The other is the output values that we want to predict, called y. The input values are also called predictors or attributes. The output value is called response. We can think of it in terms of a function, as the predictors being the independent variables and the response being the dependent variable. In machine learning, we assume that there is some function f that relates the input variables to the output variables. Once we assume that there is some functional relationship between the predictors x1, x2, x3 and the response y, we get a learning equation. Y equals some function of the predictors plus epsilon. The epsilon here is an error or irreducible error that's introduced because there's some error in measurement and other environmental variability. Let's look at an example to understand what is a predictor and what is a response. Download the two files housing.data.txt and housing.names. This is the file housing.names. This describes the data set contained in housing_data.txt. This is information for suburbs of Boston and the median housing price. This is the data that we'll be working with. We're trying to predict what will be the housing price in any suburb based on attributes found in the town. These include the crime rate, the number of schools, the pollution, the tax paid, and the average number of rooms in the dwelling. Let's take a look at the data. This is the data. We see that we have 8 columns. The first 7 are our predictors. And the last, med-v, is the median housing value. This is what we'll be trying to predict. We're trying to learn f so that we can learn the relationship between the predictors and the response. How we go about it depends upon what we're trying to do. In a prediction setting, we don't really care about the form of f. We just want a good, accurate predictor. So we might end up using some very complicated techniques that are not easy to interpret. In the inference setting, we just want to understand the relationship and to be able to make qualitative judgments about it. In this case, we will use simpler methods so that we can actually understand the underlying relationship. In some of the complicated methods such as SVMs or support vector machines and neural nets, one does not really understand what the actual functional form of f is. This leads us to a trade-off, the interpretability and flexibility trade-off. More complicated methods are more flexible in terms of the relationships that they can learn. but they're much harder to interpret. Less complicated models are much less flexible, but they're much more easily interpretable. These include examples like linear regression or regularized linear. Once we've decided which of the attributes we want to use as predictors and what is the response, we will build the model. However, there's a subtlety here. Because there's some error introduced due to sampling and our assumptions while building the model, we won't exactly get the functional form of f. We will estimate f. So our model will end up being a predictor that we denote by f cap. When we predict, we get the relationship that y predicted or y cap is some function determined by the estimator f cap of the predictors x1, x2, x3, so on. For now, let's forget about the details of how to build a model. There are various methods, some more complicated, others simpler, each having their own advantages and disadvantages, and choosing what model to build and use is an art in and of itself that we'll go through later. Let's assume that we've actually built a model, some estimator f cap. How do we know how well this model does? For this, first we'll need to understand residuals. A residual is simply the difference in the true value of the response and the predicted value of the response. It allows us to compute an error metric for the model. The error metric that we use is the mean squared error. The mean squared error is the sum of all the residuals squared and meaned. What that means is we take the individual residuals, square them, add them up, and then divide them by the number of observations. The lower the mean squared error, the better the model does. It is composed of one response y and only one predictor. The red dots show the raw data, and we've tried to build a model to predict y based on x. We've built two models, one represented by the green line, which is a simple linear model, and one represented by the blue line, which is a complicated 25-degree polynomial. Now, if we calculate the mean squared error on the data that we've given the models, the blue 25-degree complicated predictor estimator does much better than the linear model. Does that mean it is the better model overall? Should we stop our exercise? Maybe not. Let's see how our models do on data that they haven't been trained on. We gave each of the models 10 data points represented here in red. And here we see what the models predicted versus what the actual data is. It's apparent that the green model, the simple linear model, does much better than the blue, more complicated model. How could it be that a model has lower mean squared error on some data that it's been trained on, but for new data that it hasn't seen, it performs poorly? The answer lies in the subtlety of mean squared error. When calculating the mean squared error for test data, that is, data that the model hasn't been trained on or trained with, the error can be decomposed into two parts, variance and bias. Let's compare two models that we've built on a data. Suppose we have some data. Any estimator has two types of error, variance and bias. Bias is how systematically it overpredicts or underpredicts the values that it's trained on. Variance is how much its predictions change according to what data it's been trained on. The more complicated model is very sensitive. Its predicted values change widely depending on what values have been used to make the prediction. Thus, when it sees new data that it hasn't been trained on, its variance error is much larger. There's a trade-off that exists between bias and variance. More complicated models fit the training data better, but they have high variance. Less complicated models don't appear to fit the training data very well, but they have low variance and are more robust. Finding the best model is an act of balancing these two types of error. We'll learn how to do that. Let's go through the first exercise. This will give you a good idea of what supervised learning is, what a fitting exercise actually looks like, and will give you an intuitive understanding of bias, variance, and the way we deal with this uncertainty in measuring error of a given model. Best of luck.